Okay. Going back all the way to the beginning of this class with problem solving and even leaning back into Math 122 a little bit is the idea of a problem involving pigs and chickens type of question where you see a certain number of heads out in the yard, uh, and a certain number of feet. How many pigs are there? How many chickens? Another way to ask a question like this would be, there are bicycles and tricycles in a shop. And when counting, you count up 32 seats and 72 wheels. And then the question says, how many bicycles are there? It could also ask for how many tricycles, but this asks for how many bicycles. And there's a couple of different ways you can do this. You can do this with trial and error. You can do this with a picture, or what's most common is to do this with algebra, setting up two equations and solving. And that's the way we're going to go about it. We're going to make equation about the seats, and we're going to make another equation about the wheels. So a bicycle has one seat, a tricycle has one seat. So bicycles plus tricycles equals 32. That equation's about the number of seats that there are in the shop. And then the other equation about the wheels, well, a bicycle has two wheels, so 2 times b, which is b is the number of bicycles, plus 3 times t, since there's 3 wheels on every tricycle, is equal to 72. And now we have two equations, two variables, so we can solve. What we can do here is use a process called substitution. And we're going to go over here to this equation that has ones as the coefficients on our variables. And we can solve for either one. It doesn't really matter. I'm going to go ahead and subtract b from both sides. Over here they cancel, and that gives me that t is equal to 32 minus b. Essentially what that's saying is the number of tricycles is 32 minus however many bicycles there are, which makes sense. Now what I'm allowed to do is take 32 minus b and substitute that where the t is in the other equation. And that's what we're going to do. We're going to substitute. We're going to replace t with 32 minus b. Now I've got 2 times b plus 3 times t, but instead of t, I'm going to write 32 minus b, and that's equal to 72. And now I've got one equation with one variable, so I can solve it. First thing we'll do is distribute this 3 through those parentheses, and I'll have 2b plus 3 times 32 is 96, minus 3 times b is 72. If you see anything that you're not sure of, you let me know. We don't do a ton of algebra, so this may be a little rusty for you. Now I have like terms here with those b's, so I can combine those. I've got 2b and negative 3b, so that's negative 1b plus 96 is equal to 72. Now I want to get that b by itself, so I'm going to subtract 96 on the left, subtract 96 on the right. On the left-hand side, those cancel, leaving me with negative 1 times b. And on the right-hand side, I have 72 minus 96, which is negative 24. At this point, I'll just multiply both sides by negative 1. So b is 24. And I found out that there are 24 bicycles in the shop. This question said, how many bicycles are there? And that's what I've got right here. If the question had said, how many tricycles are there? I just have to do one more thing. I just have to go back here to this equation that I found. I know the number of tricycles is 32 minus the bicycles. Once I found out that the bicycles is 24, then the number of tricycles is 32 minus 24. So the number of tricycles is 8. So if I was asked for tricycles, I'd say 8. Since I was asked for bicycles in this one, I would say 24. Moving on to statistics, find the mean, median, mode, and range for the following data set. And we'll just kind of go through these one at a time as they're written up there. First, the mean. And remember, the mean is the thing that we commonly refer to as average. The mean is the sum of the data points divided by the number of data points. And so here we're just going to add them all up and divide by how many there are. So that'll be 12 plus 19 plus 23 plus 10 plus 18 plus 33, all divided by 1, 2, 3, 4, 5, 6, divided by 6. So let's see, 12 plus 19 plus 23 plus 10 plus 18 plus 33. That's 115 over 6. And that's 19.16666666666. I was told to round the mean to the nearest hundredth. So we'll find the hundreds place, 2 past the decimal. Look 1 space to the right, that's 5 or larger. So we'll round this up to 19.17. And that's the mean of this data set. For the median, that's going to be the number in the middle, but be careful. Before we can find the median by looking for the number in the middle, we want to make sure we rate these from least to greatest. So let's see, that'll be 10, 12, 18, 19, 23, 33. So before we find the median, make sure you write them least to greatest. And now we want the one in the middle. We know from finding the mean that there are 6 data points, which is an even number, which means there will not be one sitting there right in the middle to be our median. Instead, there will be 3 data points lower than the median, 3 data points higher than the median. And when we section that off, that's here and here. And with an even number of data points, what we have to do to find that median is find the 2 that are closest to the middle and find the mean of those. And that will be our median of our data set. At this point, you may be comfortable saying, well, halfway between 18 and 19 is 18.5, and you'd be right. But if you wanted to, you can certainly do 18 plus 19 over 2. That's 37 over 2, and that's 18.5, and that's the median of our data set. That's the number that's right in the middle. If we have an odd number of data points, then there will be a number sitting right in the middle that is our median. When we have an even number of data points, though, we have to find the 2 that are closest to the middle, and the mean of those will be the median of our data set. The mode, that's the data point that occurs the most. It's not always easy to see the mode when they're written like this, but when we write them from least to greatest, we can see if there are any that occur more than any others. Here, they all just occur once. So here, there is no mode because there's no data point that occurs more than the others. And then finally, we were asked to find the range. The range is just the highest minus the lowest. So here, that's this 33 minus this 10, which is 23, and that's our range. So for mode, range, and median, it's helpful, if not even totally necessary, to write these from least to greatest. For the mean, we don't really have to. We can just add them up and divide by how many there are. Staying in statistics, we'll look at weighted averages. We talked about this last week when we were getting ready for, our review for the final quiz, but here's a similar idea in Connie's math class. Homework counts for 10%, quizzes count for 30%, and exams count for 60%. If her scores are as follows, what's her overall percentage in the class? And the first thing we'll have to do is find the mean for each one of these categories. So for the first one up here, we have 92 plus 0 plus 83 plus 76. And that's 251 divided by 4. Be careful there. Make sure you're dividing by 4. That 0 is one of the scores, so it counts. And that's 62.75. So Connie's homework mean is 62.75. Excuse me. For quizzes, we have 94 plus 71 plus 97. That's 262. Here we're dividing by 3, and that's 87.33333333. And for exams, it's just 80. So we don't have to do any calculation there. Now we're going to take the weights that we've been given and put those to use. So homework is 10% of her grade. So her overall average is going to be 10% multiplied by her homework percentage plus 30% for quizzes. So 30% multiplied by her quizzes average. And we're not going to do any rounding until we get to the end. So we're just going to keep all those threes. As many as your calculator will let you type in there. And then plus 60% times her exam average. So we'll multiply those, and we'll have 0.1 times 62.75 is 6.275 plus 0.3 times 87. I'll just type a whole bunch of threes. We don't want to do any rounding. And I get 26.1999999. I'm actually going to leave that one on my calculator. Actually, I can't, can I? 0.6 times 80 is 48 for the exams. So now I need to add these together to get the overall percentage. Little bit inconvenient to have a non-terminating decimal like this, but that's okay. We'll just type a whole bunch of threes, what our calculator will let us put in there, and it'll be fine. So let's see. Altogether here, I have 6.275 plus 26.199999999 plus 48. And when all is said and done, I have 80.474,99999. Finally, now that I'm at the very end, at this point, I can round to the nearest hundredth. So I'll find the hundredths place. I'll look one space to the right. That's 4 or lower. So we'll round this down to 80.47. Again, as we go through these review problems, these are things we've worked on before. You may have been comfortable the first time. And if not, maybe it's like, oh, that's how do you do this one? And the light bulb's coming on now. Either way, that's fantastic. If that's not happening and you're seeing something you're not sure of where it came from or why we do it that way or how we do it, please don't hesitate to ask. It's true. We're going to cover a lot of topics today, but I don't want to make you hesitant to ask questions. Okay, moving away from statistics, we'll get into probability. Starts with counting. A license plate consists of 3 letters followed by 3 numbers. How many of these are possible if repetition is allowed? This is the fundamental principle of counting. How many choices for each stage in the problem, and multiply those together. Here we've got letter, 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 number, number, number. So that first letter, there are 26 possibilities. Letter, 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 number, number, number. The second letter is 26. The third letter is 26. The first number is 10. Remember 1 through 9 and 0. Don't forget 0. Second letter is 10, or number is 10. Third number is 10. Find the number of choices for each stage in the problem and then multiply those together. 26 times 26 times 26 times 10 times 10 times 10 is 17,576,000. We'll get some pretty big numbers for answers for questions like these, but if you think about it, that's a pretty robust license plate to have. And you could have 17,576,000 different ones. If this was done without repetition, what that means is once we use a letter, we can't use it again. Once we've used a number, we can't use it again. So we start out with 26 possible letters, but now we've used one, so we can't use that one again. We don't know what it was, but we started with 26 choices. Now we only have 25. Now I've used two numbers, or excuse me, two letters. So I can't use either of those again. So I don't have 26 to choose from. I don't even have 25 to choose from. Now I have 24 to choose from. Same philosophy with the numbers. I have 10. Now that I've used one, there are 9 available. Now that I've used 2, there are 8 available. Find the number of choices for each stage and multiply those together. 26 times 25 times 24 times 10 times 9 times 8 is 11,232,000. It's less than the other way, which we would expect since you're not allowed to have any repeats. The key here is the fundamental principle of counting. Find the number of choices for each stage, multiply those together. We also looked at permutations, and permutations are when order matters. Words like arrange or order point us towards permutation. So we read this question. We have 7 dolls and we'll place 3 of them on a shelf. How many ways can this be done? Well, this doesn't have those key words in there like order or arrange. But if you think about the scenario and what's going on here, we're going to place 3 of them on a shelf. Well, if I put them A, B, C, it's going to look different than if I put them C, B, A. That shelf is going to look different. So order makes a difference. Order matters. Also, a word like arrange, if you try to replace this with pick 3 to put on a shelf, yeah, that kind of works. But really what we're doing here is we are arranging. So it can be helpful to try to use a permutation word in there and see if it makes sense. We're going to arrange these on a shelf. Order matters. We have a permutation. Many of you probably solve a permutation like this with the permutation button on your calculator, but just in case, you never know, calculator might not do what you want it to on the day of the exam. Our formula for a permutation involves factorials and looks like this. Doing this one by hand, we have 7 total dolls, and we're going to put 3 of them on the shelf. So this is 7p3, or a permutation of 7 things taken 3 at a time. Here's where you can use your permutation button, totally fine. If you want to do it by hand, this is 7 factorial over 7 minus 3 factorial, or 7 factorial over 4 factorial, which I'm going to rewrite as 7 times 6 times 5 times 4 factorial, because I want that to cancel with the 4 factorial in the bottom. And I'm left with 7 times 6 times 5, which is 210. So there are 210 ways to put 3 of those 7 dolls on the shelf. Since we talked counting and permutations, you know what's coming next. That's combinations. There are 9 players. 5 of them will be chosen to go into the game. How many ways can they be chosen? Kind of have a nice key word here, chosen. Words like select, pick, choose, those point us towards situations where order doesn't matter. And order doesn't matter points us towards combinations. They're just going in the game. You're either going in or you're not. The order that you're chosen doesn't matter. Similar to the last one, you might be using the combination button on your calculator, which is totally fine. But we do have a formula for combinations, and it looks like this. In this particular case, let's see, we have 9 total players. 5 of them are going in the game. So 9 choose 5 would be a really informal shorthand way to say this. More formally, a combination of 9 things taken 5 at a time. All right, I'm going to go ahead and do this one by hand, just so you've seen that. We've got 9 factorial on top. On the bottom, we have 5 factorial and 9 minus 5 factorial. Simplifying gives us 9 factorial over 5 factorial, 4 factorial. Now I'm going to rewrite that numerator as 9, 8, 7, 6, 5 factorial, because I have that 5 factorial on the bottom, and those are going to cancel. The 4 factorial on the bottom, I'm going to go ahead and write that out as 4 times 3 times 2 times 1. And now I can finish this up. I can cancel those 5 factorials, leaving me with 9 times 8 times 7 times 6, or 3024 in the numerator. And I have 4 times 3 times 2 times 1, or 24 in the denominator. And then I can divide those. 3024 divided by 24 is 126. There are 126 ways the players could be chosen to go in the game. For those of you who really like canceling, if you're doing this by hand, you might have said, well, dividing by 1 doesn't do anything. Let's see, 3 times 2 will cancel the 6, and 4 will go into 8 twice. So really, all I have left here to multiply is 9 times 2 times 7. And 9 times 7, 63 times 2, sure enough, 126, the same answer that way. However you're comfortable, using the combination button, finding what's left in the numerator, what's left in the denominator, and dividing, or canceling as much as possible and dividing what's left. One of the things that we studied in probability when the problems got a little more involved were tree diagrams. A gumball machine contains 5 green and 4 white gumballs. You're going to buy 2. Find the probability of getting 1 of each, at least 1 white, and the second one is green. These are problems we're going to use a tree diagram for because we don't have single specific outcomes. This says 1 green and 1 white. It doesn't say what order those are going to come in. It's just 1 of each is really what that's saying. And because there may be more than one way to get that result, we're going to use a tree diagram. So we'll draw our tree. First gumball I'm going to buy is either going to be green or white. And we're going to put the probabilities on here. Let's see, I have 9 total gumballs. 5 of them are green, so the probability of green is 5/9, successes over outcomes. Probability of white is 4/9. Now I'm going to buy another gumball, and it's either going to be green or white. And if I'm up here, that means the first one I bought was green. So the probabilities that go with those. Now I have 8 gumballs left. I had 5 greens. I bought a green. So now there's 4 greens left. The probability of getting another green here are 4 out of 8. Probability of getting white, also 4 out of 8. On the bottom half means the first one I bought was a white one. Okay, we're going to keep that in mind when we put the other probabilities on here. So I have 8 gumballs left. Started with 5 greens, bought a white one, so there's still 5 greens in there. Started with 4 whites, bought a white. So out of the 8 gumballs that are in there, 3 of them are white. Now we have all our probabilities on our tree. We're going to do some multiplying to create our sample space. If we follow this path, that's green followed by green, we're going to multiply the probabilities along that path. 5/9 times 4/8, that's going to be 5 times 4 is 20 over 9 times 8 is 72. We're going to do the same thing along all the other paths. Green followed by white is 5/9 times 4/8. So 5 times 4, that's 20 over 72. Then we keep going down our tree, and white followed by green, 4/9 times 5/8, 20 over 72 for white followed by green. And then finally, we'll get something different down here. We get white followed by white, 4/9 times 3/8, 4 times 3, that'll be 12 out of 72. Now we've created our sample space. We've used the tree diagram to get this sample space here. We're done multiplying. There's no more multiplying to do. If there's more than one way to have a success, we might have to add some fractions, but we're done multiplying. Our first question here said, what's the probability of getting one of each? Okay, well, green, green. Nope, that's not one of each. Green, white. Yeah, that's one of each. White, green. Yeah, that's one of each. White, white. No, that's not. So there's more than one way to get one of each. I could get one of each this way or this way. And so I need to add those probabilities together. And when I do that, 20 out of 72 plus 20 out of 72 gives me 40 out of 72. So the probability of getting one of each is 40 out of 72. We write probabilities as fractions. We can also write those as decimals. If we were asked to write this as a decimal rounded to the nearest hundred, we would just divide 40 divided by 72, round to the nearest hundredth, and that would be 0.56. So as a fraction, 40 over 72. As a decimal, rounded to the nearest hundredth, it would be 0.56. Let's answer those other two questions we've got here. The next one says, what's the probability of at least one white? So anywhere there's at least one white is a success. Green, green, nope. Green, white, yes, that has at least one white. White, green, yes, at least one white. White, white, yes, at least one white. So I can have at least one white this way, or this way, or this way. So I need to add all those together. When I do that, I have 20 over 72 plus 20 over 72 plus 12 over 72 is 52 out of 72. You could reduce those if you want to, but you don't have to. You can leave them just the way they are. And then finally, what's the probability that the second one is green? Well, green followed by green. Yep, second one's green. Green, white. Nope, second one's white. That's no good. White, green. Yes, second one's green. White, white. Nope, second one was white. I could get the second one green this way or this way, so I need to add those together. 20 over 72, 20 over 72 is 40 over 72. Those tree diagram problems, a lot of students find those to be some of the most challenging problems we work on all semester long. If that's true for you, make sure you practice before you take the exam. And if you have any questions about what we did in that whole process there, make sure you let me know. All right. Expected value is when we figure out what's going to happen over the long term. A jar contains marbles. It has 3 yellow, 4 white, and 11 red. The results for a player who reaches in and picks one out, if it's yellow, they win $4. If it's white, they lose $1. And if it's red, they lose $3. And what we want to do is find the expected value for somebody who plays this game. For an expected value question, we want to write down our results and the probabilities that go with them. And here the results are either win 4, lose 1, lose 3. Those are the only things that can happen. Now we need the probability of each. A player wins $4 if they get a yellow marble. And let's see. So the probability of getting a yellow marble, that's successes over outcomes. And the total number of outcomes here, let's see, it's 3 and 4 is 7 and 11. So 18 total. The probability of getting yellow then is going to be 3 out of 18. You could reduce that, but I'm going to leave it as 3 out of 18 because I want every one of these to have 18 as the denominator, so I don't have to fool with getting a common denominator later on. The probability of losing $1 is the same as the probability of picking a white marble, and that's going to be 4 out of 18. And then finally, the probability of losing $3 is the probability of picking a red marble, which is going to be 11 out of 18. Now we just need to put this in our formula for expected value. 3/18 of the time, the player is going to win $4. 4/18 of the time, the player is going to lose $1. And 11/18 of the time, the player is going to lose $3. Now all we need to do is simplify it may be helpful to rewrite those whole numbers as fractions because we're going to have to multiply fractions here. And when we multiply, we'll have the expected value is, let's see, numerators, 3 times 4 is 12, 18 times 1 is 18. Numerators, 4 times -1 is -4, 18 times 1 on the bottom. And in the numerators, 11 times -3 will be -33, 18 times 1 on the bottom. Now I just need to add these up. I already have a common denominator, so I'm going to end up with something over 18. I just need to figure out what that is. It's going to be 12 minus 4 minus 33 is -25. So what we wind up here with an expected value is -25 over 18, but we're going to write expected values as decimals, and here we're supposed to round to the nearest hundred. So we're going to go ahead and divide. -25 divided by 18 is rounded to the nearest hundred, -1.39. So the expected value for somebody who plays this game is to lose $1.39 per play. They're not going to lose $1.39 the first time or the second time or the third time. It's over the long term, a player would expect to lose $1.39 per play. Expected value can also, along with tree diagrams, expected value can be a challenging topic. So if you saw anything in there that you're not sure of or you want to ask about, please make sure you do that. Okay. As we got to the end of our probability topic, binomial probability was one that came up, and Pascal's triangle over here was really important for us. A family wants to have 4 children. What's the probability of getting at least one girl? And what we do here is because they want to have 4 children, we look to row 4 in our triangle that has these numbers in it, 1, 4, 6, 4, 1. And now we're going to label those. We're going to label those with the number of girls they're going to have because that's what our question's about. And what this row means, what this row tells us is the number of ways for them to get no girls, 1 girl, 2 girls, 3 girls, 4 girls. If you want to be extremely explicit in your labeling, you can, even though you don't really have to. I tend to like to go ahead and put this on there too, just in case, I'm not sure what the question's going to be about. I'm not sure how many questions there are going to be. If they have no girls, then that means they had 4 boys, 3 boys, 2 boys, 1 boy, and no boys. And this is the number of ways that that could happen. That's what that shows us. Now, what we're after here is, what is the probability that they have at least 1 girl? Remember, probability is successes over outcomes. So the total number of outcomes is what we get when we add all of these together. So let's see, 1 plus 4 plus 6 plus 4 plus 1 is 16. So there's 16 different ways to have 4 children, and so that's going to be our number of outcomes. Now we just need to find our successes. And our successes here is anything that has at least 1 girl. Okay, well here that's no girls, so that's no good. 1 girl, yep. 2 girls, okay, I just wanted at least 1. 3 girls, yeah. 4 girls, yeah. So the number of successes are these, plus these, plus these, plus these. This is very similar to what we saw in the tree diagram, because I could get at least 1 girl this way, or this way, or this way, or this way. And so I need to add those all together. 4 plus 6 is 10, 4 is 14, and 1 is 15. So the probability of getting at least 1 girl is 15 out of 16. Binomial probability is a topic that as a class you did extremely well with, and I expect the same to be true here. It could be there's a little bit of jogging your memory that has to happen, shaking some cobwebs loose, but this is a topic that tended to go extremely well. All right, on to geometry. We had definitions for a bunch of different quadrilaterals. And the best way to ask questions about those definitions is with some true false questions about the relationships. When we see a true false question, the key is what we're considering is, can we find a counterexample? Because if I can find a counterexample, then I can say false. All I need is one. And so here, all rectangles are parallelograms. Well, I'm going to draw some pictures here and see, all right, can I draw a rectangle that's not a parallelogram? So there's a rectangle. I have to know what a parallelogram means. Parallelogram means two pairs of opposite sides are parallel. Yeah, that's a parallelogram. Okay, well, what if I draw my rectangle this way? Yeah, you know what? I still have two pairs of opposite sides are parallel. Yeah, every rectangle I draw is going to be a parallelogram. So in working to find a counterexample, realizing that I can't, I've convinced myself that, you know what? This statement is true. All rectangles are parallelograms. Then the second one down there says every rhombus is a rectangle. Trying to find a counterexample, so I'm going to draw the first rhombus I think of. Well, heck, that one right there, that's not a rectangle. These are not 90-degree angles. Every rhombus is a rectangle. Well, right here is my counterexample. So that's false. What makes these kind of problems much easier to manage is if you're really confident with the definitions and what it means to be a rectangle, what it means to be a parallelogram, what it means to be a rhombus, and so on. We also looked at these kinds of relationships with triangles, and we're going to use the same approach. We are going to try to make a counterexample, and if we can, great, we say false. If not, then we probably convince ourselves that it's true. Every isosceles triangle is equilateral. Okay, well, I'm going to draw an isosceles triangle. That's sort of the first isosceles triangle I think of. It has two sides that are the same. Equilateral means all three sides are the same, and this does not have all three sides are the same. So right here's my counterexample. This is false. Every isosceles triangle is not equilateral. All acute triangles are right triangles. Well, let's see here. All acute triangles are right triangles. So when I'm looking for a counterexample, I'm trying to find one of these that isn't a right triangle. Well, heck, if I look right here, each of these angles is less than 90 degrees, but that's not a right triangle. Heck, this counterexample works for both of these. And I can say false because I found a counterexample. Is it possible to have a right triangle that is acute? Well, no, because acute means all the angles are less than 90. So you can't have that in there and be an acute triangle. So that's another way to convince yourself this is false. But honestly, this picture actually gets the job done as a counterexample. When we got to the part about transformations, we talked about translations, reflections, and rotations. If we want to do a reflection, we can reflect across different kinds of lines. Horizontal and vertical were primary for us. And if we want to reflect this figure across the horizontal line, so let's see, if I want to reflect this across the horizontal line, I'm looking for a mirror image. And some of you are probably really good visually at this, and you just kind of go, well, mirror image is going to be like that. Fantastic. That's great. Others of you might be a little more systematic in your approach and say, well, I'm going to take this top corner and I have to go perpendicular to the line of reflection, same distance. I'm going to take this spot down here and go perpendicular to the line of reflection, same distance. And then maybe do that with the middle of the R, perpendicular line of reflection, same distance, and now you can draw it in there. Either way, what your image after reflecting is going to look like is this right here. Then if we're going to reflect across a vertical line, we could go perpendicular to the line of reflection, same distance away. So that's where that spot on the R is going to be. And I could go perpendicular line of reflection, same distance away. That's where that spot on the R is going to be. So when I reflect this, I'm going to have that side of the R is going to be right here. That might be enough for you to just kind of go, boop, I got the rest of the R put on there. Others might not be ready yet. It might say, well, I get that this is where that side of the R goes, but I'm not totally sure yet. What if I take where this bottom part of the R is and I go perpendicular line of reflection, same distance, and that's where the bottom part of the R is going to go. And, from here, I can kind of draw the rest of my R in. Either way, you want to end up with this as your image after we've reflected across that horizontal line. And I can see that I ignored my instructions here that said horizontal first and vertical second. It didn't matter. We just wanted to do both of them. In addition to reflections, we also did rotations. Determine the rotation image of triangle ABC if it's rotated 90 degrees clockwise about point C. All right, lots of things going on here in our instructions. We're rotating 90 degrees clockwise, so we're going this way, about point C. That means point C is fixed. Point C is not going to move. That's going to be our anchor. And I'm going to rotate 90 degrees clockwise. So I'm going this direction and I'm going 90 degrees. Something nice about 90 degrees is if it's vertical, it becomes horizontal. So we can move that and it's going to go here, and that's where A prime is going to be. And then this horizontal line is going to become vertical. And so that can go right here, and that's where B prime is going to be. And now the diagonal line, that's a little harder to work with, but really I just need to finish off my triangle, and I've rotated 90 degrees clockwise about point C. Rotations can be a little complicated, but if we just sort of imagine what's got to happen there, and even for something like this, you could take your paper and just move it 90 degrees clockwise, and you can kind of see what your finished product should look like. A little bit more with transformations. Identify the transformation that maps the green pre-image to the purple image. So we're starting with the green and we're finishing with the purple, and we just want to kind of figure out what it is that's happened here. And as I look at this one, I can see that's been reflected across that horizontal line. The one in the middle, you might instantly think, well, it's not a reflection, because if it were a reflection, if you want to think of this as a face, the face would have to be looking the other direction. So it's not a reflection. This one's a rotation. And sometimes our center of rotation is not on the figure. Sometimes it's down there, and this would be a rotation. We don't know what the degrees are. We just know it's a rotation. It's clockwise. Sometimes the rotation is outside the figure like that. Sometimes it's even inside the figure, where maybe we start there and just rotate around. And then finally over here, this one, it just went that way. This one's a translation. This is a good picture of the 3 different types of transformations that we studied. Okay, symmetry. And as we get to the more recent topics, my guess is they get more and more comfortable. That's probably true, but if not, you make sure you ask questions. When we're looking at symmetry, what we're concerned with are vertical line, horizontal line, and rotation. So as we look at this flag, we want to decide, does it have vertical line symmetry? Does it have horizontal line symmetry? And does it have rotation symmetry? And in this one, let's see, vertical line symmetry. Yeah, if I were to fold it right there, sure enough, it does land right on itself. The left side and the right side are the same. So yes, we have vertical line symmetry. Horizontal line symmetry. If I put a horizontal line right through the middle and I fold across it, yeah, this would land on itself. This has horizontal line symmetry. And then rotation symmetry. Obviously, if we go all the way around, everything is going to have 360-degree rotation symmetry. So we're never going to count that, because that one's a given. What we're looking for is, does it have a different rotation symmetry? Maybe at 90, maybe at 180, maybe at 270. And here, if I were to go halfway around, the bottom would become the top, and the top would become the bottom, and the White would stay in the middle. So yeah, this would have rotation symmetry at 180 degrees. And so this particular flag happens to have all three of those symmetries: vertical line, horizontal line, and rotation. Similar figures, these happen to be triangles. They don't have to be triangles. But if we have two figures that are similar, what we can do is find a missing side length. Here we're told those are similar, and we're looking for DE, which is this side right here. So what we want to make sure we do is correctly find the corresponding side in the other triangle. And we also want to look for a relationship between those two triangles. What I see here in these corresponding sides is 12 on the left corresponds to 8 on the right. So I can set up this proportion here that has 12 over 8 as one of my ratios, because 12 in the larger triangle corresponds to 8 in the smaller triangle. Now I'm going to do that same idea. 12 is to 8 as 15 is to DE. Make sure you're careful when you set up your proportion. I've got my big over little, and then, so it's big over little, and the parts correspond. And once I've got my proportion set up, now I can solve to find the length of DE. We'll cross multiply. 15 times 8 is 120. The other way, 12 times DE. And then the last thing we would need to do here, divide by 12 to get DE by itself. Divide by 12 on both sides. Those cancel. 120 divided by 12 is 10, and so DE is 10. We were told to round to the nearest tenth. There's no rounding to do here. It already is rounded to the 10th. If you were to put 10.0 as an answer, Canvas should consider that correct, but if it didn't, you could let me know and I'd make sure to give you credit. Dimensional analysis. Here's where we take something that we've been given and convert it to a different unit. Here, what we're told to do is convert 2 quarts to milliliters and round our answer to the nearest tenth. We've been given a unit fraction that 1 liter is 1.057 quarts, and then it's on the page here, but I would hope that you would know that there are 1,000 milliliters in a liter. Basically, the milli being 1,000, centi being 100, kilo being 1,000. Those prefixes, I would want you to know that milli goes with 1,000, centi goes with 100, kilo goes with 1,000. I would want you to know those prefixes. With that in mind, let's attack this one. We start out with the thing we've been given, the 2 quarts. Set up our scaffolding and start converting. We're going to use it for unit fraction to convert this thing. And the only unit fraction I have that involves quarts is right here. I have 1.057 quarts is 1 liter. And what I'm going to do is I'm going to put my 1.057 quarts on the bottom because I want quarts to cancel. I want these quarts on the top and the quarts on the bottom to cancel. And so my 1 liter, my 1 liter goes on the top. At this point, I've gone from quarts to liters. My units used to be quarts, now they're liters. I'm not done yet though, because I need to go to milliliters, and that's where this idea, this unit fraction comes in handy. 1 liter is 1,000 milliliters. I'll put my 1 liter on the bottom and my 1,000 milliliters on the top. The reason I put them there is because I want these liters to cancel. And now the units I have are milliliters, and since that's what I was looking for, that's how I know I'm done doing conversions. I've used all the unit fractions I need to use. I've got the units I want. Now we'll multiply across the top, multiply across the bottom. And when we do that, let's see, I get 2 times 1 times 1,000. On the top is 2,000. On the bottom, I have 1.057 times 1. And milliliters are the units I have left. Finally, we'll divide. 2,000 divided by 1.057, and I end up with 1,892, rounded to the nearest tenth, 0.1 milliliters. So we've converted 2 quarts to milliliters. All right. Percent error. This is one where we want to know, we can kind of measure how accurate a measurement really is. The formula for percent error is the amount of error divided by the actual amount. How far off is it compared to what it really is? That's how we find percent error. And here in this one, well, it's 30 foot tall, but it's measured to be 25. So the difference between those, that's our amount of error. So the amount of error here is 5. And then on the bottom, it's the actual amount. Be really careful there. Make sure you put the actual amount, not the measured amount. So that's going to be the 30. Now we just need to divide. 5 divided by 30, and I get 0.166666. That keeps going. This is a decimal answer, and what we're after here is called percent error. So we're going to rewrite this as a percent. We'll move the decimal over 2 places and have 16.66666%. And we weren't told how to round in this one. Let's just round this to the nearest hundredth. So if we round this to the nearest hundredth, we will find the hundredths place, look 1 space to the right. That's 5 or bigger, so we round that up. Our percent error here is 16.67%. All right. Perimeter and area, and here we're looking at a triangle. And this question says, a right triangle has a hypotenuse with a length 17 feet. One leg has a length of 15 feet. What is the perimeter of this triangle? And again, this one's pretty recent, so you may be pretty comfortable with it. But let's see, if I'm supposed to do something involving a triangle, I'm going to go ahead and draw a picture of a right triangle. Hypotenuse is 17, and one of the legs is 15. I need the perimeter. So what I want to do here is I want to add up all 3 sides. The problem is I don't know what all 3 sides are. The first thing I'm going to have to do is find the length of that side. Since this is a right triangle, I know I can use Pythagorean theorem here and have leg squared plus leg squared is hypotenuse squared. Now we need to solve this for x. First, we'll go ahead and simplify anything that we can. So I'll have x squared plus, let's see, 15 squared, 225, is 17 squared, 289. Now I have an equation to solve, and the way that I'll do that is I'm trying to get x by itself. So I want the term with x by itself, so I need to peel this from the outside in. I need to get rid of that 225. We'll subtract 225 from both sides. These will cancel. And let's see, I've got x squared is 64. Up next, to get rid of squaring, I'm going to square at the left. I also have to square at the right. And on the left-hand side, those cancel, leaving me x. On the right-hand side, square root of 64 is 8. And I just found that this side length is 8. Be really careful if you're asked a question like this. Kind of feels like we should be done. I drew a picture. I created an equation using Pythagorean theorem and I solved it. Feels like I'm done and I'm moving on. But hold on a minute. This question didn't say find the missing side length. It said what is the perimeter of this triangle. So I have one more step to do. I need to add up all 3 sides. My perimeter here is going to be 17 plus 8 plus 15. When I add all those together, I get 40. So the perimeter here is 40. Be really careful to not finish before the question's done. It's one of those make sure you answer the question that's being asked type of hints. Very recent, arc length. A circle has a radius of 3 inches. Rounded to the nearest hundredth, how long is the arc that is cut by a 65-degree angle? You don't have to draw a picture here, but I don't know. I usually find it helpful if we want a 65-degree angle, we're looking for that arc length right there. Important for arc length is the distance all the way around the circle, the circumference. So we'll find that first. Circumference is 2 pi r, and our radius here is 3 inches. So that's 2 times 3.14 times my radius, which is 3 inches. So our circumference, 2 times 3.14 times 3, is 18.84. It'd be inches, but we could go with 18.84 for now. And what I want to do then is set up a proportion that is, let's see, 18.84 is all the way around the circle, and 360 degrees is all the way around the circle. I want to know how much of that 18.84 would be in the arc created by this 65-degree angle. Now I've got a proportion set up, and I can solve it. We'll have S times 360, or 360 times S, is whatever 18.84 times 65 is. 1224.6. Last thing we need to do here to get S by itself is divide by 360 on the left and on the right. Those will cancel, leaving me just the S. And on the right-hand side, rounded to the nearest hundredth, we get 3.40. So how big is the arc that's cut by a 65-degree angle? 3.40 inches. Kind of makes sense. If all the way around is 18.8, then this little slice right here would be 3.4. Surface area and volume of a box. These were driven by formulas. I'm going to do volume first. The volume of a box is just length times width times height. The surface area of a box, we had to consider each piece of the box, top and bottom, front and back, left and right, and add up the area of each of those sides. And the formula that came forward for that was 2 times length times width plus 2 times length times height plus 2 times width times height. Essentially, finding surface area and volume is really about using these formulas, plugging in carefully, and then evaluating. So the first thing we'll look for is the volume, just because it's shorter. If we want the volume of this box, our volume is going to be the length, which is 8, times the width, which is 3, times the height, which is 2. 8 times 3 times 2 is 48. It's in inches. This is volume, so it would be cubic inches, but you just respond with the 48. Then we have surface area, a little more involved. Find surface area. We just have to be really careful about what we plug in and how we evaluate it. 2 times the length times the width plus 2 times the length times the height plus 2 times the width times the height. And then we'll simplify. Order of operations plays a role here. We've got to make sure we do multiplication before we do addition. And let's see. 2 times 8 times 3 is 48, plus 2 times 8 times 2 is 32, plus 2 times 3 times 2, that one I can do, that's 12, and then we add those together. 48 plus 32 plus 12 is 92. Those would be square inches because we're talking about surface area, but your answer would just be the 92. Does anybody have questions about anything we've talked about up to this point? All right. Now we get to this one, which you've seen before, and probably the last time you'll see this one. It's just a reminder about the best approach to take sort of mentally as you go into an exam and you take an exam. Please stay away from perfectionism and negative, and instead focus on realism and positive. There's an impossible amount of things to learn for this test. No, definitely not. We've talked about the main concepts, main ideas just today. And the contrast to that is, I don't need to know every question to pass. I hope you get every question right. That's what I'm rooting for. But even if you don't, you definitely don't need to get every question right to pass. And you don't even have to get every question right to get a really good grade. My knowledge of some certain topic is shaky. That may be true, but if you start studying now and ask questions when they come up for you, you can learn what you need to know before you take the exam. I always do poorly on tests. Always is a really big word. There has to be an exam somewhere along the line, a quiz, probably in this class that you've done well on. So that just probably is false. And if you go into this with a really good study plan, you can minimize the effects of that. If I don't pass this test, I'm a failure. Please never think that about any test. It's one test in one class in one semester. Don't make it into something that it's not. I'm not going to pass, I'm going to pass, but if I don't, I can bounce back. Well, we're at the end of the semester, so there's not really the bounce back. But have the attitude of, I'm going to prepare for this thing and I'm going to pass. And then this test is going to have a trick question. You might look at that one that we use Pythagorean theorem to find the side length, but the question asks for perimeter. You might see that as a trick question if we hadn't talked about it multiple times. I don't see that as a trick question at all. I promise I will not try to trick you on purpose. And this test is designed to let me show what I know. This is your last exam in Math 123. There may be a concept that you struggled with before, but now you get a chance to show that you've mastered it. And I think there's a lot of value in that. And if you go into it thinking, this is a chance for me to show what I know how to do, I'm just going to answer. You're going to ask me questions and I'm going to answer them. And that's all.